Greetings everyone, welcome into Calculus 2. We're going to be going through a whole section of advanced integration techniques for this first third of the course here. The first one, integration by parts. So if you've just reviewed or if you remember from Calc 1, you may have noticed that we never addressed the more advanced derivative structure rules as antiderivatives. For example, we did not address the product rule, we did not address the quotient rule. Okay, so here in this first lesson, we're going to address the product rule, and there is not a treatment for the quotient rule. It sort of gets swooped up in some of the other structures that we have better patterns for. But the product rule has integration by parts as its opposite, if you will. However, don't think of integration by parts as limited to being only the opposite of product rule. Integration by parts has many, many uses, and a multiplication of two functions in the integrand is just the beginning. So I'll start there, but then I'll expand and show you how there's several different main sections that we can apply this particular integration rule to. So here, we'll start with product rule so that you can see where the integration by parts setup comes from, right? Remember the derivative of a multiplication of two functions of x. Give me the product rule where I take the derivative of each one independently while leaving the other alone and adding those two results together. If I were to do the antiderivative with respect to x, that's why the dx's have gone away. I'm then doing just the integral of the differential portions. So in this case, the integral of the d of f times g, which is just going to be the f times g, right? And then, of course, I'm doing antiderivative here, which is going to give me an integral of two different multiplications. Generically, I can't simplify them, but this is where the structure comes from. What I do have is that the multiplication of f times g is a composite of these two antiderivatives, and merely I'm just going to subtract one over. So I have f times g minus the integral of g df is equal to the integral of f dg. And then this is what we use to our advantage. If I start with an integral that has a multiplication of two things, and one of them holds a differential in them, right? dg doesn't have to just be the d with some letter. This can actually be a function with a dx tagged on the end, or a dv, or whatever, okay? In general, typically integration by parts, they don't use f and g. I just started there because you're probably accustomed to that with the product rule. However, by parts, they use u's and v's. Okay, so in general, if you have some integral with a multiplication, right, u dv, and dv can be just a differential, just dx, just dy, or it can be something more complicated, multiplied times dx or times dy. Okay, this can vary in complexity, which is what I was alluding to before about integration by parts being useful for more than just multiplications. However, that is the setup that we're expecting here out the door, is a multiplication to go along with product rule. So the integral of u dv is equal to u times v minus integral v du, right? So if you think back to your substitution times, that's basically what I'm going to be doing, except this thing is insinuating that I need to substitute two different objects and also have their derivatives up front. That's where the dv and the du are coming from, just like you did with substitution. Okay, so here's an example right here. I see the multiplication, the 4x times the sine 2x, okay? That right there gives me a big flag for, this might be integration by parts. Okay, great. So the next thing that kind of throws me into that is that I see that I have something that has repetitive derivatives and something that does not. This gives me the idea that it's what we call the first category of by parts. It's the easier, the simplest kind, right? I shouldn't have said easier. They're all the same difficulty. It's the one with less moving parts. Okay, so here's what I do. I let u equal to one part. In this case, I'm going to let it equal to 4x. And then I let dv be equal to another part. Okay? So then what I'm actually doing here, if you want to see, I don't usually write these, but I need a little bit more space here. I don't usually write these. Okay. But what I'm going to do is I'm going to take and find du, and I'm going to find v. You're given u and dv in the original integral. So I've picked 4x for u, and I've picked sine 2x dx for dv. Could I have picked it the other way? Could I have put sine 2x here, and could I have put 4x dx here? Yes. Could I put the dx here with the u? No. See, dv is already a differential, so it needs to have that other differential portion as part of it. Okay? But back to the original question, could I have put the sine 2x here? Yes. But let's think about this for a second. By parts is allowing me to split these things up and sort of treat them separately for a minute. And if I have a way of getting rid of one of them, then that's the direction I want to go. And when we say get rid of, I mean, kind of think about it. If I take the derivative of 4x, I'm just going to get 4. So here, this is going to be 4 dx. And now I no longer have a variable multiplied here. It's sort of, made it simpler. Okay, so then how do I find v? Well, I know dv, so I'm going to just do the antiderivative of this sine 2x. The antiderivative of sine 2x is going to be the negative 1/2 cosine 2x. Now I have all of the pieces. So what I'm going to do is I'm going to set up my by parts integral. In other words, the integral 4x sine 2x dx is equal to u times v. So that's 4x times negative 1/2 cosine 2x. I'll go ahead and just write it out. Minus integral v times du. So that would be negative 1/2 cosine 2x. And du is 4 dx. All right, now let's simplify. This is going to be equal to negative 2x cosine of 2x. Here I've got 4 times the half is 2, and then double negative, so I'll have plus 2 integral cosine of 2x dx. And then I just have to do this integral right here, and I'm done. So then I have negative 2x cosine of 2x plus, I'm going to use the 2, actually, I should have written it this way. I should have realized. The 2 is going to be part of the antiderivative. The antiderivative of the cosine with a 2x is going to give me a 1/2, times the 2 is just going to give me 1. And so then I've got sine 2x, right, plus c, like so. And notice I did eventually get the plus c. So here is my answer to that integral. let's expand further into this first category of integration by parts. The category is whenever you have something repetitive, integral or derivative, multiplied by something that terminates with integrals or derivatives. All right? And typically what that means is something polynomial times something transcendental, sine, cosine, e to the x, those sorts of things. That's typically what you would expect from these integrals. These are the ones that we run into that this category gets used for. So I want to show you one that's the next stage up here from the first example that we just saw. And it looks pretty much the same as far as structure goes, right? I've got a polynomial, x squared, times an exponential function, e to the negative x over 3. So, you're thinking it should be the same caliber. And it pretty much is. It's like a half step slightly more complex. Not more difficult, it's just got more pieces to it. Okay, and what I want to demonstrate to you is that there's actually, for this category, there's going to be a quicker way to do this. But I'm going to show you the full-on way that has all the steps of the actual calculus behind it. And then show you how the shorter method works better. So here we go. I'm going to start with my u being x squared, and my dv is going to be e to the negative x over 3 dx. Remember, we've got to have our original pieces, and I'm picking the u to be the x squared because it's something that I can get rid of in this particular structure. When it's this kind of multiplication, that's what you're looking for. I'm going to let the u be something that I know I can take derivatives to make it weaker, right? To make it eventually go away. So then du is going to be equal to 2x dx, and v is going to be equal to negative 3 e to the negative x over 3. Right? Now let's think about that for a second. Remember, we have to divide by the thing that's multiplied in here, and technically it's a negative 1/3. And when I divide by that, I get a negative 3 multiplied on the outside here. Okay, so then my integral x squared e to the negative x over 3 dx is then equal to uv, so that's going to be negative 3x squared e to the negative x over 3 minus the integral v du. Okay, so then that's going to give me a negative 6 because the negative 3 times the 2. Integral of x e to the negative x over 3 dx. Okay, so I'm hoping that you just noticed, or maybe even a little bit before noticed, that this is still not structurally ready to be completed, because I still ended up with an integral that had a multiplication of two different structures there, the x and the exponential. However, it is weaker than the last one, right? The first one had an x squared in it, but I still need to do this one by parts also. Okay, so then I need another breakdown of just this integral right here. Okay, so just this integral right here, just this portion right here, I'm going to break again with a by parts. So I'm going to say u2, right, I'll just use subscripts. Some people use w and z and all that other stuff. I'm just going to use u sub 2. Okay, so u sub 2 is going to be equal to the x, and dv sub 2 is going to be the exponential again, e to the negative x over 3 dx. So then du2 is just going to be dx, right, derivative of the x, and then antiderivative to give me v2 is going to be it's going to be identical, not just very much, it's exactly identical to the last one we did. So I get negative 3 times e to the negative x over 3. And then I'm going to have to do that integral just by itself. All of this other stuff is still here now. Don't forget, this is part of the first by parts and is still structurally there. Right? Okay, so here I go. Integral x squared e to the negative x over 3 dx is equal to negative 3x squared e to the negative x over 3. I'm going to put plus 6, and then I'm going to put a bracket, because now I'm starting the other by parts structure here. So it's going to be uv, that's going to give me negative 3x e to the negative x over 3, minus integral v du. So I've got a negative 3 e to the negative x over 3 dx. Now, notice this integral right here, I can finish it up and complete the whole thing. Okay, so let's write in the final step here. Integral x squared e to the negative x over 3 dx is equal to negative 3x squared e to the negative x over 3 plus, okay, now actually I'm going to distribute that 6, so it's not plus anymore, right? I'm going to go ahead and distribute the 6 right here into both of these pieces. So I've got a minus 18x e to the negative x over 3. And then right here I'm going to have plus, hang on, let me go ahead and do the antiderivative real quick to show you. This is going to be plus 9 e to the negative x over 3. Because the antiderivative here is going to pop out another division by 1/3, right? Oh, and actually, it's going to pop out another negative. I almost made a boo-boo there. Because, see, I've got this negative, and then this is going to pop out another one. So it should be minus, like so. And then I have the 6 to distribute in. So that's going to give me minus 54 e to the negative x over 3. And then, of course, you have your plus c. Okay, now you can clean this up a little bit too. Sometimes people do advise that. Everything has a negative. Everything has a 3 also. Everything does not have an x, but everything does have the exponential, e to the negative x over 3. Okay, times, I'll have x squared plus 6x, and then plus, that's going to be 18, right, plus c, which is completely fine for answer. Of course, either one is completely fine for the final answer on that one. All right, so as you can see, the by parts is successful. It is very useful for an integral such as this. However, it's quickly going to get complicated if I want to do something with more and more increasingly large exponents. And that, of course, brings out a huge issue, right? What if I want to do y to the 40th? Do I really want to do 40 stages of by parts like this and fill up 10,000 sheets of paper? No. I would, of course, use my tablet and not use paper. Anyway, no, I don't want to have all that to worry about, right? Okay, so there's a shorter way to organize this. This is all of the actual calculus steps behind everything here and all the algebra and everything, but I can organize it differently in something called the tabular method. Okay? The tabular method is what I always use anytime I run into one of these category 1 by parts. Anytime I have a polynomial times something repetitive like that, I always just go straight to tabular method, even if it's x to the 1. Tabular method is just, for me personally, helps me stay more organized and takes up a lot less space the way I write too. Okay, so here's the way tabular method works. you put u and v in an old-fashioned plug and chug type of chart like this. I don't know if you remember the old plug and chug, and maybe I'm too ancient, but my teachers called it plug and chug because you'd put X and Y and you'd plug in the X's and chug out the Y's, right? But it's the same kind of thing, except I'm not plugging things in to get one or the other, okay? In this by parts, what I'm going to do is I'm going to start at the top with my original u and dv pieces. So for this integral, that would be x squared and the e to the negative x over 3. So what you want to do is you want to do the u side first. You want to go down the u side and take derivatives over and over and over and over again until you can't anymore. And little red flag here, that's why tabular method is for this particular category, because it assumes that your u side is some sort of derivative that will eventually terminate to 0. Okay, so watch. Derivative of x squared is 2x. Derivative of 2x is 2. Derivative of 2 is 0. So now I've completed the u column there. So once I have the u column, I go down the v column with antiderivatives, right? Integrals basically, to have the same number. I basically just have to fill out until I match with the 0. Okay? So antiderivative of e to the negative x over 3 is negative 3 e to the negative x over 3. Then I do another antiderivative, which would give me 9 e to the negative x over 3. Because remember, e to the x, right? It's its own antiderivative. I'm just going to keep going. And then I'm going to have negative 27 e to the negative x over 3. Okay. Next step is to put it all together and just write the answer. Watch. With tabular method, remember you have to have an offset. It has to be u times v. And technically, this original guy right here was originally a dv, right? So it's an angled multiplication. I'm going to multiply these two diagonals here. I'm going to multiply these two, and I'm going to multiply these two. So you see why I had to go to here. Anything after that would be times 0, and it's not going to have any credence. Okay, another thing, it's minus integral of v du. The minus in there is important, okay? So the first multiplication is positive because that's u times v. Then minus integral v du, so minus, and then minus minus if it comes up, right? So then it's back to plus again. You have to alternate the signs when you're doing these tabular multiplications. Watch. Now I have negative 3x squared times e to the negative x over 3. Right here. Negative 3x squared times e to the negative x over 3. Next, negative 2 times 9 is 18, negative 18, x e to the negative x over 3. Lastly, plus negative 2 times 27, which will be negative 54, e to the negative x over 3, and of course don't forget your plus c. So notice I could have skipped all of this, and from this one table set up correctly, I can just write out the answer. And that's what we really want, especially when the integrals start to get even larger. Example, y to the 4th times the cosine of 5y. I'm going to do this one by tabular method. Okay, so I'm going to set up my table, u and v, right? Got my table. I'm going to have y to the 4th, 4y cubed, 12y squared, 24y, 24, and 0. So I've gone all the way down my u column until I've terminated my derivatives to 0. Next, I'll do my antiderivatives starting with that cosine of 5y. So the antiderivative of that is going to be 1/5 times sine 5y. Then another antiderivative is going to be negative 1/25 cosine 5y. Then again, it'll be negative 1/125 sine 5y. Then another antiderivative will bounce it back to positive 1/625 cosine 5y. Right, because the antiderivative of sine gives me the negative cosine. And then I'm going to do one more. I bounce out another 5. Antiderivative of cosine is going to give me just the sine of 5y again. And I'll have 1/3125. Now to finish setting up my tabular method here, don't forget I'm going to be multiplying diagonals. So I've got a plus, I've got a minus, I've got a plus, a minus, and a plus. Right, we'll just go down alternating on in there. And I can just write down the answer to my integral now. This integral is equal to, I may not be able to fit it all in though. I'm probably going to have to go down a couple of lines. Let's see. I have y to the 4th over 5 sine 5y, minus minus, so plus 4y cubed over 25 cosine 5y, right? Plus minus, so minus 12y squared over 125 sine 5y. Okay, and then minus again, so minus 24y over 625 cosine 5y. And lastly, plus 24 over 3125 sine of 5y. And of course, don't forget your plus c. Yeah, it's a rather long answer, but definitely not one I would have wanted to go through all of the steps for. Tabular method is definitely irreplaceable in these kinds of cases. You definitely want to practice this tabular method and get it in good, because the most common by parts is these kind of by parts. Next category is a special set of functions that just work differently with by parts. And you just need to remember, whenever you come across one of these special pieces, that you have to set it up the opposite of what you have been doing or what you might think. These special functions are ln, the natural logarithm, and any of the inverse trig functions. You want to always set those to the u portion. And the reason is because whenever you take the derivative of the natural logarithm or the inverse trig functions, those derivatives change format, right? Logarithm and inverse trig functions are transcendental, but when you take their derivatives, they turn into rational and polynomial interacting types of things. Derivative of ln is 1 over x, derivative of arctan being 1 over x squared plus 1, so on and so on. These all become things that are easier to interact with once you've used the derivative instead of the integral. So for example, I want to do the integral of ln x, but I don't know any antiderivative that results in that. Although if you've watched my Calc 1 series, we do actually know this antiderivative. But let's go through and use by parts to prove the answer to this one. Okay, so what we do is we start by letting the ln be the u portion, like so. Then du is 1 over x. So then dv is just dx in this case because I've used up everything else. And therefore, antiderivative of v is just going to be x. So then I set up my by parts integration. It's going to be equal to u times v, so that's x ln x, minus integral v du, x times 1 over x dx. And yes, I did forget that one piece over here. I hope you caught me. I forgot my differential on that derivative. But then x times 1 over x is just 1, right? So really, this piece right here is just the integral of dx, which is just x. So then we can say that the integral of ln x dx is x times ln x minus the integral of dx, which is x, and then of course plus c. Same idea with something that has a higher power in it. In fact, you can even get away, with doing this exactly like one of these other ones, but I'll go ahead and do it with the by parts. I'm going to set it up where u is equal to the ln 7x to the 3, and dv is just the dx. So then du, being the derivative of this, is just going to be the derivative of this, which is your 21x squared, over the 7x cubed dx, right? But of course I can reduce that. And then what I end up with is just 3 over x, right? So du is 3 over x dx, right? I'm just going to simplify that one. Antiderivative of the v, right, gives me x. And as you can see, I'm going to end up with something very similar to the original one over here. So I do my vu, or uv, whichever way you want to look at it, minus integral v du, which is just going to be x times 3 over x, which is just going to be the integral of 3 dx. So then I end up with x ln 7x cubed minus 3x plus c. And of course, don't forget, I've been using plus c's and I've been doing indefinite integrals this whole time, but all of this still works the same way if you're doing a definite integral, right? If we have the lower and upper limits, where I would just be plugging in the upper and then plugging in the lower and then subtracting the uppers minus the lower values, right? That's the only difference. If you can do the indefinite, then the definite integral is just plugging in some numbers and doing some subtraction. Next, if I run into an inverse trig function, I think of this the same way. I'm going to let that inverse trig function be the u portion. Okay, so then my u here is equal to the inverse tangent, the arctangent of 6x. And then of course my dv is just the dx portion. So the v being x, right, makes that straightforward. The derivative of this du, of course the inside derivative is 6, so then the 6 times the 1 in the numerator. And then I have my dx. And then this squared plus 1, right? So that's 36x squared plus 1. Then I set up my by parts. So I'll have u times v, so that's going to be x times inverse tangent 6x. And you can write arctangent, inverse tangent, either way. I'm just trying to save space a little here. Minus the integral v du. Okay, so that's going to give me 6x, right? The 6 times the x over 36x squared plus 1 dx. And then I just need to worry about how am I going to perform this particular integral here. Okay, no problem. I'll just use an old school substitution. Let's use w, right? I'll let w be the 36x squared plus 1. So then dw is going to be equal to 72x dx. And I have a 6x dx. Almost perfect, right? What am I missing? I just need a times 12, right? So if I do times 12 here, I'll just need a 1 over 12 here. And this is now my 72x dx, right? Okay. So let's keep going here. I have x inverse tangent 6x. Notice this is not affected by the substitution, right? This piece was already integrated and finished. So I'm just leaving that part alone. Minus 1 over 12. And I've got the integral of 1 over w, dw. Right? 1 over w, dw there. Okay. So then next, I'll go ahead and do that antiderivative. There's tangent 6x. I've got minus 1 over 12. And then I'll have the ln of the absolute value of w plus c. And of course, then I can come back out of that temporary w universe there. And I have x inverse tangent 6x minus 1 over 12 times the ln of 36x squared plus 1 is never negative. So I don't need the absolute value. But you could put them. It wouldn't be wrong. But plus c. Okay? So again, it's that same MO where plugging in the function for the u and then doing the derivative that we already know allows it to be something that can interact in that polynomial and or rational universe that we already have many good methods for dealing with. Arc sine x is not going to be any different. I'm going to let u equal to the inverse sine, right? Arc sine, inverse sine. So then du is going to be 1 over square root of 1 minus x squared dx. And then, of course, dv is going to be just the dx from the integral. So v is x. And I can start setting up my by parts. So I'll have u times v, so that's x inverse sine x, minus integral v du, x over square root of 1 minus x squared dx. And notice, again, this comes up as a secondary substitution, something that I can do by letting my inner piece get substituted. So I will, again, use w to be 1 minus x squared. And dw is a negative 2x dx, of which I almost have, right? I've got the negative right here, you see? And then I've got the x and the dx, I'm missing the 2. So if I put a 2 here, and I'll go ahead and bring the negative in, it's going to turn this negative positive, and I'll balance the number with a 1/2. So I've got my negative 2x dx for the substitution there. I've got x inverse sine x plus 1/2 integral. Now this is going to be 1 over the square root of w. So in other words, w to the negative 1/2 dw there. And then I'll just integrate that, right? Okay. So x inverse sine of x plus, I'm going to get w to the 1/2 and then divide by 1/2. You see it? I'm going to get w to the 1/2 when I add 1, and then I have to divide by that new power 1/2. So that ends up dividing away, and all I've got is just w to the 1/2. But what's w? It's 1 minus x squared. So then I finish up with rewriting it back in its original form, like so. All right. Let's keep going with this second category with some more examples that also have other parts besides just the ln or the anti or the inverse trig function. Okay, so x to the 5th times ln x, the integral of x to the 5th ln x dx. Right, so again, remember when you see one of those specials like ln x, you have to remind yourself, hey, wait a minute, I want to do the derivative of that one so that I can let it cross back over and interact better with my polynomial. So when I set this one up, I've got u is going to be equal to the ln x portion, and dv is going to be the x to the 5th dx. So then my du is going to be 1 over x dx, and then my antiderivative v is just going to be 1/6 x to the 6th. So then I set up my by parts by doing u times v, which is going to give me 1 over 6 x to the 6th ln of x minus the integral v times du. Well, notice I'm going to have that 1 over 6 again, right? But then x to the 6th times 1 over x is just x to the 5th. And then the dx is still there. But then this is just a straight power rule antiderivative. So I can easily finish it out. I have 1 over 6 x to the 6th ln x minus, this is going to give me 1 over 36 because I'm going to divide by the new power again when I get x to the 6th. And of course plus c. And don't forget, you can actually clean these up a little bit if you so choose. You notice that in this case, both of these have the x to the 6th here. So I could easily clean this up by pulling out a 1 over 36, x to the 6th. And then, of course, that would leave me with 6 ln x minus 1. Either one of those is fine. Well, okay, what if I've got some sort of radical and even a denominator type power dealing with an ln? No different. I'm still going to approach this like I want to let my logarithm be the u portion, the portion that's going to get the derivative. So ln of x squared, and therefore my du is going to be 2 over x dx. So then my dv is going to be equal to the rest of it. Now, of course, this is in the denominator and it's a third root, so that's x to the negative 1/3 power dx. And then I do my antiderivative of that. V is going to be x to the 2/3 because I add 1, 3 over 3 to negative 1 over 3. And of course I have to divide by that power, so I have 3/2. Alrighty, next I set up my by parts. I have u times v, so that gives me 3 over 2 x to the 2/3 times the ln of x squared minus the integral v du. So I have 3 over 2 times 2 over x. The 3 over 2 times the 2 of course, is going to give me just a 3. And the x to the 2/3 times the x to the -1 is going to bring me back down to x to the -1/3 again. Right? Don't forget, I'm just going to be multiplying this times this, basically dividing, which means I subtract the powers, right? 2/3 minus 1 gets me back to the -1/3 again. Alrighty, so then I can finish this up by doing that power rule integration, like so. I'll have minus, and then 3, of course, right? Times the 3/2 again, x to the 2/3, plus c. Of course, I could turn this into 9/2, but also another way to clean this up would be to go ahead and factor this out. I've got a 3/2 x to the 2/3 times ln of x squared minus 3 plus c. Of course, either one of those is fine as long as you do your multiplication of the 9/2 there. So now, same idea, but with an inverse trig function, right? Okay, so I'm going to set up my u and v. U is going to be equal to the arctan. Remember, it's one of those special ones, so I'm going to go ahead and let him be the u portion here. And then that means my dv is the x dx, right? The x dx portion there. So then du is equal to the 1 over x squared plus 1 times dx. And the antiderivative here is x squared over 2, right, for the v portion there. So now let's actually set up the by-part structure. I've got u times v. So then the overall integral is equal to, I'll write the 1/2 x squared this time, inverse tan of x, minus integral v du. Alrighty, I'm going to pull the 1/2 out here from this, and then I've got x squared times this fraction, so I get x squared over x squared plus 1 dx. And I just need to facilitate that last antiderivative there. Okay? This one is a little bit less complicated than it seems. For me, what I do is this. Since I notice these already match, and all I'm missing is a plus 1 for them to completely match, I go ahead and put it plus 1. But of course, I can't just put a plus 1. I'm also going to, right next to it, put minus 1. Okay? Now that's in the numerator. It's not multiplied. It's x squared plus 1 minus 1. But what I'm going to do with that is I'm going to split it into these two fractions. I'm going to have x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. That's what I'm actually going to do with that. Because you see what's happening is I'm then going to match this, right? And I just took the minus 1 as his own fraction with that denominator. Okay. So then I have 1/2 x squared arctan of x minus 1/2 integral. This over itself is 1. And then I've got minus the 1 over x squared plus 1 and then dx. So now both of those are antiderivatives that I can recognize right away, right? Integral of 1 is just x. Integral of 1 over x squared plus 1, that's arctangent. So 1/2 x squared times inverse tangent minus 1/2 times x minus inverse tangent x, and then of course plus c. I can regroup this a little bit, but notice I can pull a 1/2 out of everything. Okay, that's what I'm going to go ahead and do. I'm just going to pull a 1/2 out of everything. That leaves me with an inverse tangent that's multiplied times, I see an x squared, but also notice I have a negative inverse tangent here. So that's plus 1, right? Negative is plus. I pulled the 1/2 out. So it's really just plus inverse tangent there, right? So times 1. And then what else is left? I have the minus x. And everything's times 1/2, right? Plus c at the end. Doesn't seem like it'd be the antiderivative of the x times inverse tangent. It kind of does, but then you're like, go ahead and take the derivative. You'll see that this product rule cranks out something that gives you this thing, and then plus 1, and then the derivative here is minus 1, wipes it out, right? So it actually is the antiderivative of that. Now it's time for that third category that I was talking about, or that I alluded to before, with by parts. This is one that comes up every so often, but it is important for you to know that it does exist. And in one of the 3 examples, and 2 here, 1 in the next scene, one of the 3 examples that I'm going to be doing here, as I'll repeat again in a minute, is going to be important when you get to the next section as well. So this third grouping is whenever you have something that has a lot of repetitive functions embedded, and you attempt to do a by parts, and then at the very next stage you realize that you're getting a repeat in your structure. Either it'll be exactly the same or something very close, and what you want to do is you want to follow that repetition until you get back to where you started. And then we can use a quick algebra technique to just sort of sew it up succinctly in one nice little package. Okay, so let me show you these 2 examples, and then I'll do a bigger example in the next scene. Sine of the ln of x, right? So a little composition there. Obviously I can't do a substitution. There's no thing for the derivative with the ln of x portion there. So that part's not going to work. However, what I can do here is I can go ahead and set this up with a by parts the same way we were treating the last few, and I'm just going to let the function be the u portion that I know I can do the derivative of. All right, so I'm going to let u equal the sine of ln x portion, and then of course that means that the dv is going to be equal to just the dx. All right, so then my v is going to be equal to x, right? Okay, and then my du is going to be derivative of this is a chain rule now, so I'll get the outside, which is going to be the cosine of ln x, and then the derivative of the inside, the derivative of the ln x, I'll have times 1 over x, and then of course I'll still have my dx there, right? All right. The other thing that you want to do with this one is, just to make it a little bit easier on myself, I'm going to let the integral equal a. And this will become apparent in a moment why I'm just sort of simplifying the structure here by letting this be represented by the capital letter A there. Okay, so I set up my by parts, which means I have a is equal to, right, because that integral is equal to u times v, so that's going to be x times the sine of ln of x, minus the integral of v times du. Notice what happens. The x times the 1 over x wipes out, and all I'm left with is the cosine of ln x dx. So right here, this should be a little red flag for this might be that third type of structure. Like I said, when you get some sort of repetition in your structure, which notice it's almost identical to that original integral, right? I have a cosine this time though instead of a sine, so it's not exactly the same. And then that sort of beckons me to just continue with the pattern, because what's going to happen after I do a derivative of the cosine, right? I'll get back around to sine again, in which case I'm going to end up with what I started with, and that's what you want. Ending back up where you started will allow us to use our finisher algebra technique. Okay, so here I'm going to go again with a second round of by parts. And in this round 2, I'll let u2 again equal to, don't change your pattern, I let u equal the complex function before, I'm letting it equal the complicated function again. Okay, so then that means dv2 is going to be dx, which means v2 is going to be x, just like before. And u2, the du2, again, is the derivative here. Derivative of cosine is negative sine of ln x. And again, I'm going to get times 1 over x, so I'll just put over x, dx, right? So I've got my by-part structure ready to go again. So I'm going to continue here. Okay, so a is still over here, right, is equal to x times the sine of ln x minus, now I'm going to set up for this integral here. I'm going to do u times v, so that's x cosine of ln x minus, now be careful, this minus right here distributes, okay? So I have minus minus, and then integral v du has yet another minus, okay? So I have 3 minuses, 3 negatives, all occurring right here. I've got the one that's being distributed, I have the one from the second by parts, and then I have the one being multiplied in. So the 3 negatives is going to land me with a negative again. Integral v du, the x over the x again wipes out, and I'm left with sine of ln of x dx. And just as we thought, we came back around in our pattern to that same integral that we started with, right? Okay, so bear with me. This is what I've got. I have a equals x sine of ln x minus x cosine of ln of x minus a. Remember, we let that equal to a? I have an a over here also, don't I? So this is what I do. I add that to both sides. And it gets rid of it here, right? So I have 2a is equal to x sine of ln x minus x cosine of ln of x, like so. But I want to know what a is, not 2a, so I just divide everything by 2. So a is equal to 1/2 times x sine of ln x minus x cosine of ln x. And of course you could factor out the x if you wanted to, or whatever makes you more comfortable, or you could distribute the 1/2 in. But regardless, I have solved for a, which is what we let our original integral equal to. So this must be the antiderivative. Just don't forget your plus c, right, at the very end. A would of course be equal to this portion, and then the integral itself would have to have the plus c has his antiderivative, unless you were doing a definite integral, in which case, plug in your numbers and subtract by whatever you mean necessary. Okay, so that's that third type, when you see that repetitive structure. This is sort of the same thing. I'm going to get something repetitive, but it's not going to repeat in the same kind of way as that one. And that's because secant doesn't actually work the same way sines and cosines do. But I will get some sort of repetition in there that will allow me to still perform my little algebra technique at the end here, where I bring something over and then have just the leftover as the answer. Okay, so secant cubed. Here's what I do. I let u equal to secant of x, and I let dv equal to secant squared x dx. Now let's pick that apart for just a second and think about it. I would separate it like this because I don't really want to do a derivative of the whole secant cube. That would be a really disaster mess. However, derivative of just the secant is great. And secant squared happens to be one of my antiderivatives that I already know, so that also fits really nice. So that's why I've split it like this, because I recognize the secant squared. By the way, if you have any integral where there's a secant squared floating around, it's probably a good idea to try this direction. If it ends up being something you can't resolve, then you go back and try something else. But if you see something with a secant squared, this is a good way to approach it, letting the secant squared be the dv portion. Antiderivative of secant squared is just tangent. And then derivative of secant is secant times tangent, right? Dx. Okay? So, just like before, I'm going to let my integral equal something like a. And that, again, that's just for simplifying the structure. It just makes it easier to notice what I have to do. So then when I set up my by parts, I have u times v. So I have a is equal to, don't forget, right? It's the integrals equal to secant x tangent x, that's u times v, minus the integral v du. That's going to give me secant times tangent squared dx. Because I already had a secant tangent, right, in the du, and then multiplying another tangent just gives me that. Okay, now it's time to play around with the structure of my trig. And what I'm noticing is that tangent squared is by itself equal to secant squared minus 1. It's Pythagorean identity of my trig stuff there, right? Okay, so then right there, I have a secant times that. I'm just going to distribute that secant. Okay, also, well, wait, I'll just do it in a couple of steps. So I have a is equal to secant x tangent x minus the integral of secant cubed, because secant times secant squared, minus secant dx. So you should get a little excited right there. Ooh, I'm seeing the repetition. There's my secant cubed. But wait a minute, it's tied together. Well, that's okay, right? It's addition and subtraction. That's okay. I can separate integrals on that. Okay, so this is what we've got. I have a equals secant x tangent x minus, now look, the integral of the secant cubed dx, that's a, right? And then negative, negative, plus integral of just the secant part, secant x dx. Well, that's an antiderivative that we can do. If you're not familiar with that one, it's one of those quick and dirty rules that you have to know. And I explain it in one of my Calc 1 videos dealing with the antiderivatives of trig functions. Okay, so if you're not sure, go take a look at that one. Again, I have my algebra trick here, my technique, I mean, where I'm just going to add that to both sides. And that's going to get rid of it over here. And that's going to leave me with 2a is equal to secant x times tangent x plus the antiderivative of secant x is the ln of the absolute value of secant x plus tangent x plus c. Right? Now divide everything by 2 and I've got a. So a is equal to 1/2 times secant x times tangent x plus natural log absolute value of secant x plus tangent x plus c, which would be the answer to my integral of secant cubed because it's equal to a. All right? So to finish up this lesson, I want to do one more example of that third type of by parts usage. And you can almost see this one right away just by looking at it. I have two different derivative and integral repetitive types. So sine, you get cosine sine, no matter which way you go, derivative or antiderivative. Exponentials, same thing, right? They're very repetitive in their derivatives and integrals. So I'm not going to be able to do anything that terminates in this situation. And I know I'm going to have to be looking for some sort of pattern where it repeats back on itself. And I'll be able to use that little algebra technique to sew it up into a nice, neat package. Okay, so like before, if I notice that it needs to be one of those pattern ones, I go ahead and let it equal to some, letter. I'll just use a. And I will set up a by parts. So in other words, I'm going to let u equal something and dv equal something else. I'll just let u equal the sine of 3x, and I'll let the dv equal e to the 5x dx. It really doesn't matter in this case which one you let be which one, but I am going to have to do two stages. The one thing you don't want to do is change in the middle. So once I've made this decision to let these things be that pattern, I want to repeat that pattern, exactly the same setup again. Okay, so here we go. du is going to be 1/3 cosine of 3x dx, right? And v, when I do my antiderivative here, I made a boo-boo. I hope y'all caught me. Should be 3, not 1/3. Antiderivative here should be 1/5 e to the 5x. Okay, so I'm going to set up my first by parts here, and I'm going to let a equal u times v. Okay, so I've got 1/5 sine 3x e to the 5x, right? U times v minus the integral of v du. So I'll have 3/5 cosine 3x e to the 5x dx, right? Okay, so at this point it should be really solid. Yes, I see the repeating pattern because I have the exact same structure type of integral. It's just that it's a cosine now instead of a sine. And then I should be anticipating, oh, well, if I just go through this one more time, then maybe I can make it wrap back around and repeat the same integral again, in which case I can button it up, right? So I'm going to, of course, factor the 3/5 out, and I'm just going to let my second stage be between the cosine and the exponential there. Like I said before, whatever pattern you pick before, the pattern I want to pick again. So cosine 3x, since I let that one be sine 3x, so du2 is going to be -3 sine 3x there. Make sure I keep track of those signs, -3 dx. Next, dv2, right, is going to be equal to e to the 5x dx. Therefore, v2 is 1/5 e to the 5x. All right. So my next level here, I have a is equal to 1/5 sine 3x e to the 5x minus 3/5 times. Now that, I'm going to go ahead and separate it out. Now I'm setting up the second by parts. uv, so that's 1/5 cosine 3x e to the 5x minus integral v du. So that actually gives me a plus 3/5. Look at it, 1/5 times -3, right? Okay. And the 3/5 is then sine 3x e to the 5x dx. And just as we thought, we would wrap back around and see that integral again. There's that sine 3x e to the 5x, right? Except it has the 3/5 on it. Okay, so I'm going to go ahead and distribute and get the structure ready. So then I've got a is equal to 1/5 sine 3x e to the 5x minus 3/25. Look, -3/5 times 1/5. Cosine 3x e to the 5x. Now, -3/5 times 3/5. I'm bringing this 3/5 out because I don't need it in that integral. So I have -3/5 times 3/5, so that's -9/25. Okay? Times a. See it? Because this is that same integral, and I brought the 3/5 out, so now it's identical to a, and I just multiplied the other -3/5 times it. So this is what I've got. Now what I need to do is use my algebra technique to button it up. So I will add 9/25 a to both sides. So what does this give? I have 25/25. It's 1a plus 9/25, right? So 25 and 9 give me 34/25 a is equal to 1/5 sine 3x e to the 5x minus 3/25 cosine 3x e to the 5x, like so. And of course, then to simplify this, what I'm going to do is I'm going to multiply both sides by 25/34. So all of this I need to multiply by 25/34, which of course will reduce, some of my pieces here. And also don't forget the plus c at the end. So a is equal to 25/5 gives me a 5 in the top over 34 sine 3x e to the 5x. 25/25 goes away, and I'm left with minus 3/34 cosine 3x e to the 5x, and of course plus c is equal to a, which was what my original integral was equal to. Okay, so I hope that this lecture has helped you understand all of the different ways that we can apply this one rule, this integration by parts. There's actually even a couple more little intricacies that might pop up every now and then that I didn't talk about here. You just need to remember the basic structure of the biparts formula and how you can maybe puzzle solve the pieces that you have in your integral to make it fit. Integration by parts sometimes is like solving a puzzle. It's like putting together the pieces of something that you've never seen before. And you may have to play with it. You may have to try one way, and if it doesn't work, try it another way. And if that doesn't work, then that's when it's time to move up to one of the methods that we'll be talking about later on in this chapter. Okay?